Hey guys, good morning. Welcome to the Aerospace Structures lecture series. This is Professor Devan, Department of Aerospace Engineering. Today we're going to see the deflection of beams, bars, truss, frame, and other structural members which are used in the aircraft structures by using of strain energy method. In last class, we discussed about what is strain energy method, in particularly due to axial load, bending load, shear load, and torsion load. So deflection of strain energy method. This method is also called as real work method, since work done by the external loads are considered. From the law of conservation of energy, strain energy is equal to real work done by the load. That is, strain energy is equal to summation of half times the average load into the deflection. And this equation can be used to find out the deflection in the beams and frames subjected to bending stresses. Strain energy method can be used to find deflection under the following situation. Structure is subjected to a concentrated load. Deflection required is at the loaded point and is in the deflection of the load. Let us take this problem using strain energy method. We can determine the deflection of free end of the cantilever beam of length L subjected to a concentric load P at the free end. So the load is P, the distance is L. Taking bending moment at a distance x from the free end will get m equal to P into x. Strain energy formula U equal to 0 to L m square by 2 EI into dx. Integral of 0 to L m will be P into x. So if you are applying m square, you are getting P square x square by 2 EI into dx. So P square by 2 EI is a constant, whereas variable x will be, by integrating, we are getting x cubed by 3. So applying the boundary 0 to L, we are getting P square L cubed by 6 EI. So work done by the load is equal to half times load into deflection delta. So therefore, the strain energy U equal to work done is equal to P square L cubed by 6 EI, which is equal to work done by the external load, that is half P into delta. So from this delta deflection, we'll get PLQ by 3EI. Using strain energy method, determine the deflection under the 60 kilonewton load in the given beam structure. So this is the second problem. Here we are going to find the deflection of this beam, that is A to B, B to A to C. So here the A to B, that is a cross section, is EI, whereas A to C is 2EI. The length of the beam, the entire beam is 8 meters span, and the applied load at the midpoint is 60 kilonewton. So solution for this beam, reaction RA plus RB, RA is equal to RB equal to 60 kilonewton. Therefore, bending moment at any distance x from the A point, at the R at the point x from the B point, we are getting 30x into kilonewton. So strain energy U equal to 0 to L m square by 2 EI. Here we are getting strain energy is equal to, for the span AB, 0 to 4, 30 into x square and 30x square by 2 EI into dx, plus span BC, integral of 0 to 4, 30x square divided by 2 times of 2 EI into dx. By solving this, we are getting U equal to 14,400 by EI while applying the limits 0 to L or 0 to 4. Work done by the load W equal to half time into P into delta. We are equating this to the find out the value of 40,400 by EI is equal to half time 60 into delta. Delta we are getting, that is deflection, 4 divided by EI. Coming to the third point of the frame, using strain energy method, determine the vertical deflection of a point C in the frame shown in the figure, E equal to 210 kilonewton per mm square, and moment of inertia I equal to 30 to the number of 6 mm power 4. Here we are in AB and BC span. AB of length is 2L, 2I, and B to C equal to I. The load 1 kilonewton acting at the point C. So detail of this beam expressed for the various portion of the structure. is calculated individually for the member BC, then for the member AB, and the given data in the table form at a portion AC, BC, and AB, origin will be like C and B. For BC, limit will be 0 to 3, by because length of the beam is 3. For AB beam or AB span, the limit is 0 to 4. The expression can be written as for BC span is 1x equal to x, whereas portion AB equal to fixed value 3. Integrating of say, finding strain energy U equal to 0 to L m square by 2 EI. Here we have to find the two different span, that is A to B, B to C. 0 to 3 x square by 2 EI to dx plus 0 to 4 3 square by 2 EI into 2y into dx. By solving this, we are getting strain energy equal to 13.5 by EI. Equating the strain energy equal to work done, that is half times load into delta. We are getting delta equal to 27 by EI, whereas metal property E and E equal to 210 gigapascal and I equal to the given value of the member. So we are getting delta equal to 20,000, 27 by 6,000. The reflection of this particular frame will be 4.5 mm. Next, we are going to the strain energy method using the one more method, that is horizontal deflected on roller and the deep for the portal frame shown in the figure. EA equal to 80,000 kilonewton meter square throughout the member, that is AB, BC, and CD. So here also we are going to find out the limits, origins, and the moment, that is A to B. We have the origin equal to B, B to C, the origin equal to C, C to D, the origin is D. Limit will be 0 to 4, 0 to 3, 0 to 4, that will be length of the member, and moment will be 5 into x, 20 into x, 20x minus 5x. Applying the energy equal to m square by 2 EI for the first member, that is 0 to L 5x by 2 EI the whole square into dx plus 0 to 3 20 squared by 2 EI into dx plus interval of 0 to 4 20 minus 5x the whole square minus 2i. By solving this, we are getting 1133.33 by EI. Work done equal to half times load into delta. We are getting 2.5 deflection. Finally, we are obtaining the work done is equal to delta equal to 453.33 by EI. By substituting EI equal to 8,000. So finally, we are getting 56.7 mm deflection. So thank you. We'll see in the next class.